let's talk about enzyme inhibitors. And if you're following along with your pre-party, you just learned about the first kind of enzyme inhibitor, which those that are irreversible. Remember, the organophosphate compounds will bind to the active site of an enzyme via a covalent linkage that they inactivate the enzyme. Literally, the enzyme is killed. But we also have reversible enzyme inhibitors. So let's focus for a minute on those. Reversible enzyme inhibitors are of a couple of different types. We're going to focus mostly on competitive inhibitors. Now, competitive inhibitors, just as you might guess, are those that compete with the substrate for binding site, binding to the active site of the enzyme. So if we draw a cartoon in which this is the active site, competitive inhibitors compete with the substrate. So if our red molecule is a substrate, we know that it likes to bind to the active site, but a classical competitive inhibitor will look much like the substrate and will compete for binding at the active site. So that being said, we can write our trusty equation where we take into account the presence of this competitive inhibitor. So I'm going to erase our cool cartoon so that then we can write out our trusty equation. And recognize that the inhibitor competes with the substrate for binding to the active site. So we have to consider this alternative in which the enzyme would become bound to inhibitor instead of substrate. Now we could give this a constant, Ki. Your book uses capital I. I often use lowercase I. Either is fine. So we can recognize that both substrate and inhibitor are vying for that pole position, that active site binding position. So there is a competition going on. Now, what this means is that because that competition is always occurring, it's going to cause the enzyme to appear to desire its substrate less. So we could say that in another way, right? That is, recall that Km is a measure of the enzyme's affinity for substrate. So if we think about our good old trusty graph of initial velocity as a function of substrate concentration, when we have the typical situation, there is nothing out there to compete with substrate for binding to the enzyme active site, and so we have our typical function. However, in the presence of inhibitor, there's going to be a lot more competing for binding to the enzyme's active site. So the enzyme is going to appear to desire its substrate less, or said another way, the apparent Km of the enzyme is going to increase. So if we find our Vmax over 2, if this is Vmax, I didn't use my ruler here, so this is probably a little bit of an estimation. So we would recognize that if this is Km in the absence of inhibitor, then when we add inhibitor, we would expect that apparent Km to increase. That is, said another way, the enzyme will appear to desire its substrate less. because, of course, it's all caught up with trying to bind to two different things, and so there's a lot of competition going on. We call this the Km apparent. Now, we can go ahead and write the Michaelis-Menten equation for in the presence of an inhibitor, considering this Km apparent. So let's go ahead and write that equation. So this is the equation as we know and love for the original function in the absence of the inhibitor. However, when we are in the presence of inhibitor, we know that the value for Km is going to be dictated by the presence of inhibitor. So in order to express the apparent Km, we will write Km in a different way. So Km apparent is going to be equal to something that we're going to call alpha Km. Now, alpha Km is simply defined as a factor, alpha, times the Km. We know that that factor alpha always has to be has to give Km a larger value. In fact, alpha is defined as 1 plus the concentration of inhibitor over the Ki. Now, a quick look at that will tell us that alpha will, of course, tell us that if the concentration of inhibitor is 0, that is, there is no inhibitor, then we know that this term will go to 0, this most right-hand term, and, of course, then alpha will be equal to 1 if no inhibitor. Of course, the more inhibitor is present, then we know the greater that alpha value will become. Now, said another way, if we really think about this, alpha is the factor by which the substrate must be increased in order to overcome the effect of the presence of the inhibitor. So that makes sense, doesn't it? Because in order to overcome the presence of the inhibitor, then the substrate concentration is going to have to be higher to get to the Vmax over 2, right? So we could think about that as being the factor, right? That factor by which that substrate concentration has to increase is in fact the ratio of Km apparent over Km, right? That's the factor alpha. Oh, yeah, got it. That makes sense because the amount that the substrate concentration has to increase by to overcome the presence of inhibitor. Okay, cool. So we can give some definitions then to alpha. Now, we can actually now we're equipped to calculate the Ki if needed with the information that we now have. But before I leave this behind, it's really important to note that competitive inhibitor, while it's changing the apparent Km, it is not impacting the Vmax because we can still see that this red function eventually can approach maximal, and it's doing it, it's just slower about it, and it can eventually approach Vmax. Now, this is important because what it means, if we write down a take-home message, is that competitive inhibitors increase apparent Km, but do not affect Vmax. So they do their inhibition inhibiting by affecting the apparent affinity of the enzyme for its substrate, rather than by affecting its potential maximal velocity. So now let's use what we have figured out here to display and utilize the Lineweaver-Burk plot. So remember when we ended class off last time, we had learned how to use the very convenient double reciprocal plot, or Lineweaver-Burk plot, where we took the 1 over the initial velocity as a function of 1 over the substrate. And remember that that allowed us to get a linear function in which we could note that the intercept, the y-intercept, is 1 over Vmax, and the x-intercept, of course, is negative 1 over Km. Now, we wrote a trusty equation for that. Slope of the line, Km over Vmax. And we now can do that in the presence of inhibitor as well. So let's go ahead and draw what happens in the presence of inhibitor, right? We know Vmax doesn't change. It's unaffected. So it's going to pass through that same y-intercept. But we know that apparent Km goes up. So on a double reciprocal plot, that means it will come closer to the 0 and gain a steeper slope. So this is, of course, the blue there is without inhibitor. And the green plus inhibitor. Oh, great, awesome. And so we're recognizing that the apparent Km, so negative 1 over Km parent, or of course we could express that as negative 1 over the alpha Km. And we could modify then the equation for our line. Cool. So this is fantastic because it gives us an expression for both with and or without and with inhibitor, and a recognition of the impacts of classical competitive inhibition. It additionally is really cool to think about the fact that we can actually calculate the Ki, because that may be important. Like if we want to know what is the affinity of the enzyme for its inhibitor. So if we actually know Km values, so say that we know that we have an enzyme that has a Km value that is equal to, say, for example, 8 micromolar. And then if we know that the Km apparent, like we can actually measure it, and of course Km apparent is what we would see if we didn't know, we just measured Km and we saw this, but we didn't realize there was an inhibitor present. So if that equals 12 micromolar. So this is cool because remember then that alpha is that factor. So remember that alpha is the factor by which the substrate must increase in order to overcome the presence of inhibitor, or said another way, right? It's the ratio of the Km apparent over the Km. And then that factor of alpha is equal to 1.5. And then, of course, also remember the equation that we had for Ki. So if we recall, We also had this equation that relates alpha to the Ki, so 1 plus concentration of inhibitor over Ki, and we know alpha now, so we can actually solve for Ki. So we can recognize then that, come over here, Ki is going to be equal to the concentration of inhibitor over alpha minus 1. So, of course, we would have to know the concentration of inhibitor. So if we knew that we had added 3 micromolar of inhibitor, then we could calculate the Ki, so moving arrow, Ki is equal to 3 micromolar over alpha, which was 1.5 minus 1, which of course then is 0.5. And so we can get the Ki as equal to 6 micromolar. Cool. So a lot of neat things to understand about classical competitive inhibition. Now that we understand more of the nuances of competitive inhibition, I want to challenge you to ponder 2 other types. And these are uncompetitive and non-competitive. And perhaps non-competitive is actually better called mixed inhibition. Now, we're not going to ponder these in as great a depth or with as many nuances as we did competitive inhibitors, but I do want to say a few notes about them. So in uncompetitive inhibitors, the inhibitor binds only to an enzyme that has already bound its substrate. So let's erase some things here, and then we can ponder how we might show that on our equation. So we might then say that inhibitor now can bind to the enzyme substrate complex. And we might give that the inhibition constant of Ki prime, just differentiating it. And then you get the formation of enzyme substrate with inhibitor. And of course, when that inhibitor is bound, it does something to the enzyme to render it catalytically inert. So we could even draw kind of a cartoon where the enzyme is bound to its substrate, so that substrate is firmly bound. And now the inhibitor can come in and bind, and maybe it binds to some other site, and when it does so, it makes changes that sort of have a domino effect, leading to a lack of catalytic ability of the enzyme. So recognize then that this kind of inhibitor is having an impact on that velocity or maximal, the Vmax. So if we go ahead and draw just a quick drawing of the Lineweaver-Burk plot, we're going to see this having a very different look. So R1 over initial velocity, 1 over substrate. And we will recognize that with added inhibitors, so if this shows without inhibitor, then with added inhibitor, we recognize that the Vmax will be lowered. Now, so if this is plus inhibitor, so that is the reason for the impact of a non-competitive inhibitor on the activity of the enzyme, or the reason that it is no longer able to catalyze the reaction. One thing that's important to note here is recalling the fact that this is 1 over km and a parent km, negative 1 over km and negative 1 over km apparent, is that it actually slightly increases the enzyme affinity for its substrate, but the impact of inhibition comes from the impact on Vmax. So, or we could also make note that the slope of the line is unchanged, so Km over Vmax is unchanged in the presence of uncompetitive inhibitor. So let me now just leave you to ponder maybe additional ways in which you might want to think about writing Michaelis-Menten equations and whatnot for this scenario, but I just want to say one quick word about the mixed inhibition. So if we can erase this, and consider a mixed inhibitor, which what we would say with that is that it basically there's an impact on both the binding of the substrate and the catalysis. So we are seeing a little bit of both going on here. So plus inhibitor here, and we might just say that in a mixed inhibitor, we see both the Ki and the Ki prime describing inhibition, that we are actually seeing both of those being a factor. And so when we look at our Lineweaver-Burk plots in this case, we're going to recognize that we're going to see an impact in which we see decreased affinity of the enzyme for its substrate. So recognizing if we go from no added inhibitor to added inhibitor, we're going to see that Km increasing. But additionally, we know we're going to see an impact on the Vmax as well. So we know we're going to see that value decreasing, so going from not added to added. So what we would recognize then is both an impact on slope and an impact on intercept for these mixed inhibitors. And then take a look at the one that has the inhibitor added. We now recognize that there is both an impact on the X and the Y intercept with increasing addition of inhibitor. So this becomes even more complex. So I challenge you, if you would like, to think even more deeply about the mathematical expressions describing these, but for our purposes, we're going to make that a wrap.